Hello. In this video, we're going to look at the beginnings of power series. So what is a power series? A power series centered at zero is a series, like we've looked at before, of the following form. You'll have a sum as n equals 0 to infinity of some collection of constants, c sub n, times x to the n, where x is holding the place of a variable. And so this is the sum of some constant C0 plus C1 times x plus C2 times x squared plus C3 times x cubed, so on. We call these C's the coefficients of the series. And you can think of this as a generalization of the notion of a polynomial because we have a sum of powers of x, some coefficient on each one of them. And an important thing to note is we do start the index for these power series. They start at 0 typically, and that's because we want to have a constant term C0. Now, for each fixed value of x you could think of, you could plug it into this expression, and then you'd have some series of the form c sub n times that particular number, the n, and that's a series that's a sum of numbers, and you could determine whether that series converges or diverges. For instance, we could have a series and plug in 2 for x into a series c sub n, so c sub n times 2 to the n, look at the sum of that for n goes 0 to infinity and see if that series converges. And depending on what the c sub n's are, what sequence those represent, that might or might not converge. So oftentimes a power series will converge for some values of x, but not for all. And we're actually going to learn that a power series will always converge for at least one value of x. So let's look at this example to get a feel for what I mean when I say some x's make the series converge and some don't. Let's look at this sum, n equals 0 to infinity of x to the n divided by n plus 1. So we're talking about the following sum. It's powers of x always divided by 1 greater than the exponent. So we really have 1 over 1 plus x over 2, x squared over 3, x cubed over 4, and so on. So I'm going to try figuring out for what x this converges by using the ratio test. And the ratio test is useful because it tells me, once I do that limit, exactly what values for which the thing converges, and so I can compare it to that as long as I get a value less than 1. So here I've taken the limit as n approaches infinity of the value of the sequence when I plug in n plus 1, and that's the top, so x to the n plus 1 over n plus 1 plus 1, and then divided by the nth term of my series, which would be x to the n over n plus 1. So I'm taking the limit of that quotient, so I flipped the second fraction because dividing by a fraction is the same as multiplying by its reciprocal, and then I resorted the two pieces. So I took the x to the n plus 1 part and wrote it over the x to the n, and then the n plus 1 portion I wrote over the n plus 2. So I've got the n's and the x's together. What would I get? Well, x to the n plus 1 over x to the n is x. Within the absolute value, then that's the absolute value of x. The n plus 1 over n plus 2, those were positive numbers, so I can take them outside of the absolute value. And then I'm just going to use techniques of taking limits of sequences, namely dividing everything in sight by n in this case, in that quotient, n plus 1 over n plus 2. And that's how I determine that the limit of this quotient of consecutive terms, my ratio of consecutive terms from my power series, would end up always equaling the absolute value of x times 1, or just absolute x. Now, what if we use the root test? Let's see that we'd actually be able to derive the same result in this case. It's not always the case. You could use both tests, but if you can, they should give you the same result. So the nth root test would say, okay, let's take the limit of the nth root of the absolute value of this expression, x to the n over n plus 1. So that's the same as taking both the numerator and denominator to the 1 over n power, which would leave me with just absolute x on top because it's raised to the n and then to the 1 over n. And then in the denominator, I would have n plus 1 raised to the 1 over n. Now, that limit is 1. And in case you didn't remember why, I want to remind you that's a L'Hopital's rule technique. So we rewrite n plus 1 to the 1 over n as e to the log of that expression, which allows us to rewrite the log part as log n plus 1 over n, which is in infinity over infinity form. I apply L'Hopital's rule, I get 1 over e raised to the limit of 1 over n plus 1 over 1. So that's the limit of 0 over 1, and therefore e to the 0, which is 1. So that's the reason that I'm getting the same result, that I was able to replace the limit of n plus 1 to the 1 over n with 1. And in both ways, I've determined that the ratio and root test are telling me what comes out is the absolute value of x, where remember, I don't know what x is. Okay, so I have this result, absolute x. Now, the ratio and root test both tell me it should converge absolutely, the series I'm talking about, as long as what I got out of the test is a number less than 1. And it'll diverge if I get a number greater than 1. So in this case, I'm saying I'm going to have absolute convergence. My series will converge when absolute value of x is less than 1. So like, for instance, I have the example here of if x is 0.3, the test will return 0.3 because that's the absolute value of 0.3. And so if I were to stuff that in for x in the series, I'd be talking about the series 0.3 to the n over n plus 1. That series converges. When the absolute value of x equals 1, the test is inconclusive though, because the ratio and root test, both of them, don't give you a result when that limit of that ratio, or the limit of the nth root, returns 1. So we're going to have to consider what happens in these two cases separately. Well, if the absolute value of a number x is 1, the number is either positive or negative 1. So let's consider x equals 1 first. We would be looking at the series of 1 to the n over n plus 1. So 1 to the n is just 1. So the sum of 1 over n plus 1 and equals 0 to infinity. What I've done is I just started plugging in each of the consecutive values of 1 and n and seeing what I got. So that was 1 over 0 plus 1, 1 over 1 plus 1, 1 over 2 plus 1, 1 over 3 plus 1. And that means you actually have written out the harmonic series. We know that series is divergent. So we can conclude that if x were 1, the series I've written above will not converge. What about x equals negative 1? Well, that's generating an alternating series, negative 1 to the n over n plus 1. Therefore, we can hit it with the alternating series test. Now, the corresponding b sub n would just be 1 over n plus 1, which will certainly decrease because the quantity of the denominator will increase as n gets larger. So we do have decreasing sequence. And additionally, the limit of 1 over n plus 1 is 0. So we have satisfied the conditions of the alternating series test, and we conclude that this power series does converge when x is negative 1. So to conclude, what values of x make this series converge? If I replace x with any number from closed bracket negative 1 up until 1, so including negative 1 and everything up until I get 2, but not including positive 1, then that series will converge.